Now we're gonna keep working on this geometric random variable, and we're gonna prove that the probability of the coming from the probability mass function of the random variable, the geometric random variable, is a probability mass function. So x is our geometric random variable here, and p given by this one here, 1 minus p to the power k minus 1 times p, is a probability mass function. Okay, so in discrete case, instead of calling it probability density function, we call it probability mass function. Okay, and that means in our case we will have to prove that this definition that we have given to p x, I'm gonna put a dot here, so that means any value is bigger than 0. Okay, and also the sum of these probabilities, 1 minus p to the power k minus 1 times p, where k is going from 1 to infinity, is equal to 1. Okay, if I satisfy these two conditions, that means I have a probability mass function. Okay, so in this case, our p, the big P, small p is the probability. Okay, so that means I can, if I wanna use some elementary properties, so I can prove this one very easily, starting from this definition here. So I have p is bigger or equal than 0. So p is between 0 and 1, and therefore it's bigger than 0. 1 minus p is bigger than 0, because p is let's prove it in fact. So p is between 0 and 1. Okay, so minus p is between minus 1 and 0, and 1 minus p by adding 1 to both sides is between 1 and 0. Okay, so here I proved these two. So what I have, this one, 1 minus p to the power k, is between 0 and 1 to the power k, which is 1, and p is between 0 and 1, and therefore when I do the multiplication, I still have p times 1 minus p to the power k is bigger than 0. Okay, so I verified the first condition. So p bigger than 0, that means p, the probability mass function, is bigger than 0. Okay, now I can show that this sum is 1. Okay, one key idea here is that to do so, we need to apply the definition of the sum of the series. Okay, so in this case, we take the nth partial sum. Okay, so we can write this one here, the sum of 1 minus p to the power n minus 1 times p. So I'm using n because we are used to n when we are dealing with series. Okay, so this one by definition is the limit as n goes to infinity of the Sn. What's Sn? Sn is the sum of the ak, k going from 1 to n. In our case, ak is 1 minus p to the power k minus 1 times p, and therefore I have Sn as the sum of p times 1 minus p to the power k minus 1, where k is going from 1 to n. So let's simplify this one before we take the limit here. So here I can take the p outside because it doesn't depend on n, and I have 1 minus p to the power n minus 1, k minus 1, where k is going from 1 to n. So here I can write this one. This is a geometric series, by the way, and I have 1 minus p to the power n over 1 minus p. This gives me 1 minus p to the power n over p. Okay, don't forget that I have a p that I'm not using here, that's in the front, so I'm using just this one here. Okay, here I'm using just this sum here, the ak. So if I multiply by this this p here, this is the one that I have. Okay, so if I multiply by p here, I'm gonna have, let's multiply here on this side by p, so I'm gonna have 1 minus 1 minus p to the power n. So this is my Sn. Okay, now the sum, this sum here, okay, is 1 minus p to the power n minus 1 times p as n goes from 1 to infinity. So it's the limit of Sn as n goes to infinity. Here I can take, let me take the limit here. So when I take the limit of 1 minus p to the power n as n goes to infinity, what's gonna happen? Here I have 1 minus the limit 1 minus p to the power n as n goes to infinity. Here 1 minus p is between 0 and 1, and therefore, okay, when p is 1, it's 0. Okay, so we exclude the case when p is 1. Okay, and when p is less than 1, so this one is a ratio that's less than 1. When I take the power n, I get 0. Therefore, I have 1 minus 0, which is 1. Okay? And therefore, this proves that my sum here is 1. Okay? And now I have shown these two values, show that p, big P, is bigger than 0, and the sum here is 1. This means that this geometric random variable which has this distribution given by 1 minus p to the power k minus 1 times p is a probability mass function. Okay, we are using series to see that series can help a lot. Okay, if you see any errors or any mistakes, please let us know. Please share, comment, and subscribe. Thank you.